Hello. All right, welcome everybody. Let's give everyone a moment to get back in the audience. And all right, great. Welcome to Tesla AI Day 2022. We've got some really exciting things to show you. I think you'll be pretty impressed. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot suit. But we've come a long way, and it's I think compared to that, it's going to be very impressive. We're going to talk about the advancements in AI for full self-driving, as well as how they apply to more generally to real-world AI problems like a humanoid robot, and even going beyond that. I think there's some potential that what we're doing here at Tesla could make a meaningful contribution to AGI. And I think actually Tesla's a good entity to do it from a governance standpoint, because we're a publicly traded company with one class of stock, and that means that the public controls Tesla, and I think that's actually a good thing. So if I go crazy, you can fire me. This is important. Maybe I've gone crazy. I don't know. Yeah, so we're going to talk a lot about our progress in AI, Autopilot, as well as progress with Dojo. And then we're going to bring the team out and do a long Q&A. So you can ask tough questions, whatever you'd like, existential questions, technical questions, but we want to have as much time for Q&A as possible. So let's see, with that, you guys want to say anything?
Hey guys, I'm Milan. I work on Autopilot and the Tesla Bot.
And I'm Lizzie, mechanical engineer on the project as well.
Okay. So should we bring out the bot?
Before we do that, we have one little bonus tip for the day. This is actually the first time we try this robot without any backup support, cranes, mechanical mechanisms, no cables, nothing.
Yeah.
I want to do it with you guys tonight, but it's the first time, so let's see.
You ready? Let's go.
I think the bot got some moves too. So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
This is literally the first time the robot has operated without a tether. Was on stage tonight. So the robot can actually do a lot more than we just showed you. We just didn't want it to fall on its face. So we'll show you some videos now of the robot doing a bunch of other things, yeah, which are less risky. Yeah.
We should close the screen, guys.
Yeah.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot and just walking around and dancing on stage. Just humble beginnings, but you can see the autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah, when you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up. Yeah.
We use the same process as we did for autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more. Something that we'll try to nail down in a few months, over the next few months, I would say, to perfection.
This is really an actual station in the Fremont factory as well that it's working at.
Yep. So.
And that's not the only thing we have to show today, right?
Yeah, absolutely. So what you saw was what we call Bumble C. That's our sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's done an incredible job. And we actually have an Optimus bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it out.
Do it.
Yeah. So here you're seeing Optimus with with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom. So it has opposable thumbs and both left and right hand. So it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. And we've also designed it using the same discipline that we use in designing the car, which is to design it for manufacturing such that it's possible to make the robot in high volume at low cost with high reliability. So that's incredibly important. I mean, you've all seen very impressive humanoid robot demonstrations, and that's great, but what are they missing? They're missing a brain. They don't have the intelligence to navigate the world by themselves. And they're also very expensive and made in low volume. Whereas Optimus is designed to be an extremely capable robot, but made in very high volume, probably ultimately millions of units, and it is expected to cost much less than a car.
I'll just bring it directly to the right here.
I would say probably less than $20,000 would be my guess.
Okay.
The potential for Optimus is, I think, appreciated by very few people.
Hey.
As usual, Tesla demos are coming in hot. So,
Okay, that's good. That's good.
yeah. The team's the team has put in an incredible amount of work, working days, 7 days a week, burning the 3 a.m. oil to get to the demonstration today. Super proud of what they've done. They've really done a great job. I just like to give a hand to the whole Optimus team. So, now there's still a lot of work to be done to refine Optimus and improve it. Obviously, this is just Optimus version 1. And that's really why we're holding this event, which is to convince some of the most talented people in the world, like you guys, to join Tesla and help make it a reality and bring it to fruition at scale such that it can help millions of people. And the potential, like I said, is really boggles the mind, because you have to say, like, what is an economy? An economy is sort of productive entities times their productivity, capita times output, productivity per capita. At the point at which there is not a limitation on capita, it's not clear what an economy even means at that point. An economy becomes quasi-infinite. So what taken to fruition in the hopefully benign scenario, this means a future of abundance, a future where there is no poverty, where you can have whatever you want in terms of products and services. It really is a fundamental transformation of civilization as we know it. Obviously, we want to make sure that transformation is a positive one and safe. But that's also why I think Tesla as an entity doing this, being a single class of stock, publicly traded, owned by the public, is very important and should not be overlooked. I think this is essential, because then if the public doesn't like what Tesla's doing, the public can buy shares in Tesla and vote differently. This is a big deal. Like, it's very important that I can't just do what I want. Sometimes people think that, but it's not true. It's very important that the corporate entity that makes this happen is something that the public can properly influence. And so I think the Tesla structure is ideal for that. And like I said, self-driving cars will certainly have a tremendous impact on the world. I think they will improve the productivity of transport by at least a half order of magnitude, perhaps an order of magnitude, perhaps more. Optimus, I think, has maybe a 2 order of magnitude potential improvement in economic output. It's not clear what the limit actually even is. But we need to do this in the right way. We need to do it carefully and safely, and ensure that the outcome is one that is beneficial to civilization and one that humanity wants. This is also extremely important, obviously. So, and I hope you will consider joining Tesla to achieve those goals. At Tesla, we really care about doing the right thing here, or aspire to do the right thing, and really not pave the road to hell with good intentions. And I think the road to hell is mostly paved with bad intentions, but every now and again there's a good intention in there. So we want to do the right thing. So consider joining us and helping make it happen. With that, let's move on to the next phase.
Right on. Thank you, Elon. right, so you've seen a couple robots today. Let's do a quick timeline recap. So last year we unveiled the Tesla Bot concept, but a concept doesn't get us very far. We knew we needed a real development and integration platform to get real life learnings as quickly as possible. So that robot that came out and did the little routine for you guys, we had that within 6 months, built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. So this guy is rooted in the foundation of sort of the vehicle design process. You know, we're leveraging all of those learnings that we already have. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form. We think that matters for a few reasons. But it's fun. We spend a lot of time thinking about how amazing the human body is. We have this incredible range of motion, typically really amazing strength. A fun exercise is if you put your fingertip on the chair in front of you, you'll notice that there's a huge range of motion that you have in your shoulder and your elbow, for example. Without moving your fingertip, you can move those joints all over the place. But the robot, you know, its main function is to do real useful work. And it maybe doesn't necessarily need all of those degrees of freedom right away. So we've stripped it down to a minimum sort of 28 fundamental degrees of freedom, and then of course our hands in addition to that. Humans are also pretty efficient at some things and not so efficient in other times. So for example, we can eat a small amount of food to sustain ourselves for several hours. That's great. But when we're just kind of sitting around, no offense, but we're kind of inefficient. We're just sort of burning energy. So on the robot platform, what we're going to do is we're going to minimize that idle power consumption, drop it as low as possible. And that way we can just flip a switch and immediately the robot turns into something that does useful work. So let's talk about this latest generation in some detail, shall we? So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue our electrical system. So now that we have our sort of human-based research, and we have our first development platform, we have both research and execution to draw from for this design. Again, we're using that vehicle design foundation, so we're taking it from concept through design and analysis, and then build and validation. Along the way, we're going to optimize for things like cost and efficiency because those are critical metrics to take this product to scale eventually. How are we going to do that? Well, we're going to reduce our part count and our power consumption of every element possible. We're going to do things like reduce the sensing and the wiring at our extremities. You can imagine a lot of mass in your hands and feet is going to be quite difficult and power consumptive to move around. And we're going to centralize both our power distribution and our compute to the physical center of the platform. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So that means everything from sensing to fusing, charge management, and power distribution is all in one place. We're also leveraging both our vehicle products and our energy products to roll all of those key features into this battery. So that's streamlined manufacturing, really efficient and simple cooling methods, battery management, and also safety. And of course, we can leverage Tesla's existing infrastructure and supply chain to make it. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So as you know, Tesla already ships full self-driving computers in every vehicle we produce. We want to leverage both the autopilot hardware and the software for the humanoid platform, but because it's different in requirements and in form factor, we're going to change a few things first. So we still are it's going to do everything that a human brain does, processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well. But before we do that, I'd like to introduce Malcolm, who's going to speak a little bit about our structural foundation for the robot.
Okay. Thank you, Lizzie. Tesla have the capabilities to analyze highly complex systems. They don't get much more complex than a crash. You can see here a simulated crash from Model 3 superimposed on top of the actual physical crash. It's actually incredible how accurate it is. Just to give you an idea of the complexity of this model, it includes every nut, bolt, and washer, every spot weld, and it has 35 million degrees of freedom. Quite amazing. And it's true to say that if we didn't have models like this, we wouldn't be able to make the safest cars in the world. So can we utilize our capabilities and our methods from the automotive side to influence a robot? Well, we can make a model, and since we had crash software, we're using the same software here, we can make it fall down. And the purpose of this is to make sure that if it falls down, ideally it doesn't, but it's superficial damage. We don't want it to, for example, break its gearbox and its arms. That's equivalent of a dislocated shoulder of a robot. Difficult and expensive to fix. So we wanted to dust itself off, get on with the job it's been given. We can also take the same model and we can drive the actuators using the inputs from a previously solved model, bringing it to life. So this is producing the motions for the tasks we want the robot to do. These tasks are picking up boxes, turning, squatting, walking upstairs. Whatever the set of tasks are, we can play to the model. This is showing just simple walking. We can create the stresses in all the components. That helps us to optimize the components. These are not dancing robots. These are actually the modal behavior, the first 5 modes of the robot. And typically, when people make robots, they make sure the first mode is up around the top single figures, up towards 10 hertz. The reason to do this is to make the controls of walking easier. It's very difficult to walk if you can't guarantee where your foot is wobbling around. That's okay if you make one robot. We want to make thousands, maybe millions. We haven't got the luxury of making them from carbon fiber and titanium. We want to make them from plastic. Things are not quite so stiff. So we can't have these high targets. I call them dumb targets. We've got to make them work at lower targets. So is that going to work? Well, if you think about it, sorry about this, but we're just bags of soggy jelly and bones thrown in. We're not high frequency. If I stand on my leg, I don't vibrate at 10 hertz. People operate at low frequency, so we know the robot actually can. It just makes controls harder. So we take the information from this, the modal data and the stiffness, and feed that into the control system. That allows it to walk. Just changing tack slightly, looking at the knee. We can take some inspiration from biology, and we can look to see what the mechanical advantages of the knee is. It turns out it actually represents quite similar to 4-bar link, and that's quite non-linear. That's not surprising, really, because if you think when you bend your leg down, the torque on your knee is much more when it's bent than it is when it's straight. So you'd expect a non-linear function. And in fact, the biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically a 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be a bit more scientific. We've played all the tasks through this graph. And this is showing picking things up, walking, squatting, the tasks I said we did on the stress. And that's the torque seen at the knee against the knee bend on the horizontal axis. This is showing the requirement for the knee to do all these tasks. I've then put a curve through it, surfing over the top of the peaks, and that's saying this is what's required to make the robot do these tasks. So if we look at the 4-bar link, that's actually the green curve, and it's saying that the non-linearity of the 4-bar link has actually linearized the characteristic of the force. What that really says is that's lowered the force. That's what makes the actuator have the lowest possible force, which is the most efficient. We want to burn energy up slowly. What's the blue curve? Well, the blue curve is actually, if we didn't have a 4-bar link, we just had an arm sticking out of my leg here with an actuator on it, a simple 2-bar link. That's the best we could do with a simple 2-bar link. And it shows that that would create much more force in the actuator, which would not be efficient. So what's that look like in practice? Well, as you'll see, well, it's very tightly packaged in the knee. You'll see it go transparent in a second. You'll see the 4-bar link there. It's operating on the actuator. This is determining the force and the displacements on the actuator. I'll now pass you over to Konstantinos to tell you a lot more detail about how these actuators are made and designed and optimized. Thank you.
Thank you, Malcolm. So I would like to talk to you about the design process and the actuator portfolio in our robot. So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. We are carrying over most of our designing experience from the car to the robot. So in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process. This is one of the scenarios that the robot is capable of doing, which is turning and walking. So when we have this torque speed trajectory, we lay it over an efficiency map of an actuator, and we are able, along the trajectory, to generate the power consumption and the energy, cumulative energy for the task versus time. So this allows us to define the system cost for the particular actuator and put a simple point into the cloud. Then we do this for hundreds of thousands of actuators by solving in our cluster. And the red line denotes the Pareto front, which is the preferred area where we will look for our optimal. So the X denotes the preferred actuator design we have picked for this particular joint. So now we need to do this for every joint. We have 28 joints to optimize, and we parse our cloud. We parse our cloud, again, for every joint spec, and the red axis this time denote the bespoke actuator designs for every joint. The problem here is that we have too many unique actuator designs, and even if we take advantage of the symmetry, still there are too many. In order to make something mass manufacturable, we need to be able to reduce the amount of unique actuator designs. Therefore, we run something called commonality study, which we parse our cloud again, looking this time for actuators that simultaneously meet the joint performance requirements for more than one joint at the same time. So the resulting portfolio is 6 actuators, and they show in a color map at the middle figure. And the actuators can be also viewed in this slide. We have 3 rotary and 3 linear actuators, all of which have a great output force or torque per mass. The rotary actuator in particular has a mechanical clutch integrated on the high-speed side angular contact ball bearing, and on the high-speed side and on the low-speed side a cross-roller bearing, and the gear train is a strain wave gear. There are 3 integrated sensors here and a bespoke permanent magnet machine. The linear actuator The linear actuator has planetary rollers and an inverted planetary screw as a gear train, which allows efficiency and compaction and durability. So in order to demonstrate the force capability of our linear actuators, we have set up an experiment in order to test it under its limits. And I will let you enjoy the video. So our actuator is able to lift a half-ton, 9-foot concert grand piano. And this is a requirement. It's not something nice to have, because our muscles can do the same when they are direct driven. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague, Mike, who's going to talk to you about hand design. Thank you very much.
Thanks, Konstantinos. So we just saw how powerful a human and a humanoid actuator can be. However, humans are also incredibly dexterous. The human hand has the ability to move at 300 degrees per second. It has tens of thousands of tactile sensors, and it has the ability to grasp and manipulate almost every object in our daily lives. For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hand as well. The converse there is pretty interesting because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. And that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors. You just heard how we went about designing the Tesla Bot hardware. Now I'll hand it off to Milan and our autonomy team to bring this robot to life.
Thanks, Mike. All right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months, thanks to the amazing work that we've done on Autopilot over the past few years. Most of those components ported quite easily over to the bots environment. If you think about it, we're just moving from a robot on wheels to a robot on legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from Autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the Autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. Another interesting problem to think about is, in indoor environments, mostly with that sense of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. We also did quite some work on the simulation side. And this is literally the Autopilot simulator, to which we've integrated the robot's locomotion code. And this is a video of the motion control code running in the autopilot simulator, showing the evolution of the robot's walk over time. And so as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months. And so locomotion is specifically one component that's very different as we're moving from the car to the bot's environment. And so I think it warrants a little bit more depth, and I'd like my colleagues to start talking about this now.
Thank you, Milan. Hi, everyone. I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking which are challenging from an engineering perspective. For example, physical self-awareness. That means having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy-efficient gait. You can imagine there's different styles of walking, and all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally, but as engineers or roboticists, we have to think about these problems. And in the following, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bots, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages. It starts planning footsteps and ends with the entire motion for the system. And let's dive a little bit deeper in how this works. So in this video, we see footsteps being planned over a planning horizon, following the desired path. And we start from this and add then foot trajectories that connect these footsteps using toe off and heel strike, just as humans do. And this gives us a larger stride and less knee bend for high efficiency of the system. The last stage is then finding a center of mass trajectory, which gives us a dynamically feasible motion of the entire system to keep balance. As we all know, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Thank you, Felix. Hello, everyone. My name is Anand, and I'm going to talk to you about controls. So let's take the motion plan that Felix just talked about and put it in the real world on a real robot. Let's see what happens. It takes a couple steps and falls down. Well, that's a little disappointing. But we are missing a few key pieces here, which will make it walk. Now, as Felix mentioned, the motion planner is using an idealized version of itself and a version of reality around it. This is not exactly correct. It also expresses its intention through trajectories and wrenches. Wrenches are forces and torques that it wants to exert on the world to locomote. Reality is way more complex than any sim or model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled dynamics, which essentially the planner doesn't know about, and that causes destabilization, especially for a system that is dynamically stable like biped locomotion. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And state estimation, here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model We use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
Hi, everyone. My name is Eric, robotics engineer on TeslaBot, and I want to talk about how we've made the robot manipulate things in the real world. We wanted to manipulate objects while looking as natural as possible, and also get there quickly. So what we've done is we've broken this process down into 2 steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead. Next, Milan's going to talk about what's next for the Optimus TeslaBot. Thanks.
Thanks, Eric. Right, so hopefully by now you guys got a good idea of what we've been up to over the past few months. We started having something that's usable, but it's far from being useful. There's still a long and exciting road ahead of us. I think the first thing within the next few weeks is to get Optimus at least at par with Bumble C, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories, and really going to try to nail this down and iron out all the elements needed to deploy this product in the real world. I was mentioning earlier, indoor navigation, graceful fall management, or even servicing, all components needed to scale this product up. But I don't know about you, but after seeing what we've shown tonight, I'm pretty sure we can get this done within the next few months or years, and make this product a reality and change the entire economy. So I would like to thank the entire Optimus team for all their hard work over the past few months. I think it's pretty amazing. All of this was done in barely 6 or 8 months. Thank you very much.